Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about acid-base titrations. So this is kind of continuing our conversation of what happens when I mix together an acids and a base into a solution. Well, it turns out one of the most common ways to mix acids and bases is in the form of a titration. So what we're really going to be looking at is what happens to the pH as I add a titrant, so that's whatever is in the burette that we're monitoring the volume of, to a analyte. So this is going to be a known amount of a substance that's going to usually exist in a volume in a Erlenmeyer flask or in a beaker. And usually there's going to be some sort of pH probe or chemical indicator that will tell us what's happening to the pH of the solution as we go along. So we're going to be categorizing our titrations into three major components. So the first of which is a strong acid, strong base titration. This typically happens when I add a strong base to a strong acid. The next one is a weak acid, strong base. So this is the classic KHP titration that we did last semester, where you have a weak acid in solution that I add a strong base like sodium hydroxide. This is incredibly useful in trying to either determining the number of moles of my weak acid that I have or the concentration of my strong base. Then lastly, we have a strong acid weak base titration. So this is where I'm going to try and figure out something about a weak base solution, such as many of our salts like sodium acetate. This time the weak base ends up in the analyte, and our titrant is going to be the strong acid. And one of the reasons why we place the strong acid here is that it will have a known relation with how much protons will be released in the case of a strong acid, or how much hydroxide in the case of the strong base. And you'll be able to see this as we go through our major titrations. It is worth noting there is one last type of titration that we really won't deal with because it is a lot more unusual, and that's a weak acid, weak base titration. And this gets a lot more complex as weak acids and weak bases have a very interesting and dynamic relationship. Now let's go ahead and start with the simplest of these three titrations. What happens when I add a strong base to a strong acid? So we can go ahead and examine this by looking at titration curves. So these titration curves show us what the pH will be at each individual amount of titrant added. In this case, since our titrant is our strong base, we can see the pH slowly increasing as I add sodium hydroxide, which makes sense as sodium hydroxide is a base, so I would expect the pH to go up. So we can go ahead and look at this titration by breaking it down into four key regions. So the first of which will be before I add any of my titrant. So in this case, I just have a strong acid in solution and no base. So we can go ahead and find the pH just using a strong acid calculation. Then I can go ahead and add increasing numbers of sodium hydroxide, and as I add more base, I will start consuming this strong acid as the pH goes slightly up and up and up as I have less strong acid in solution. Then we have a drastic increase of pH once we get near what's called the equivalence point. And it's called such because this will be the point at which I have equal moles of acid and equal moles of base. A key feature, no matter what sort of titration you're performing, is the equivalence point is often associated with a drastic increase in pH. Then, once we get past the equivalence point, the solution is going to be dominated by excess amount of base. I will have consumed all of my acid, and I am essentially just having decreasingly diluted base. As I keep adding more and more base, I essentially have less and less excess water present. Now let's go ahead and examine the details of this titration by breaking it down into these key 4 points. What happens before I add any base, when I add a little bit of base, when I add an equal amount of base as my acid, and when I have a ton of extra base present. So the first of these situations will be, let's say I have, I'm adding 0.1 molar NaOH to 25 milliliters of 0.1 molar HCl. So the first of these cases is simply going to be what's going to be the pH before I add any of my titrants. So this will be that starting point. What's my pH initially before I really do anything? So in this case, I don't have any sodium hydroxide, so my system just is composed of 0.1 molar HCl. Well, this is a strong acid system, so HCl will completely break apart into an equal amount of protons. So a system that starts in 0.1 molar HCl quickly becomes 0.1 molar of free protons or hydronium. And once I know the concentration of protons, I know the pH of the system using negative log of the proton concentration. In this case, if I start with 0.1 molar protons, I have a pH of 1. So what we're going to do is use this as our starting point. We're going to start with a pH of 1, and as I add sodium hydroxide, we're going to watch that pH increase. So let's go ahead and see what happens if I add 10 milliliters of sodium hydroxide. So before I do anything else, I have to figure out how my sodium hydroxide and HCl will interact. And to do that, I need to know how many moles of my base and my acid I have in the system. So I can get the moles of my base simply by doing volume times molarity. I will have added about 1 times 10 to the negative third moles, or it's often convenient in this case to use millimoles. So I will have added 1 millimole of sodium hydroxide, and we can do something similar to our HCl. Volume times molarity will produce 2.5 times 10 to the negative third moles of HCl, but because we hate exponents, this can also be referred to as 2.5 millimoles of HCl. So now I know the amount of sodium hydroxide and HCl I have. I can go ahead and feed this into an ice table. So this will tell me how much of my HCl will react with the sodium hydroxide. Again, making use of the fact that a strong acid and a strong base will always completely react with each other till one of them is completely consumed. So the key trick here is trying to identify who's my limiting reagent. So I know that both HCl and NaOH will decrease as I produce more of sodium chloride, as the sodium and the chloride want to hang out together with the other byproduct being water. So since I have less sodium hydroxide, and this is a 1-to-1 stoichiometry, I should run out of NaOH first. So this will give me an X of 1 millimole, meaning I produce 1 millimole of sodium chloride and have 1.5 millimoles of HCl left behind. So now I've got an excess of 1.5 millimoles of HCl, no base, salt, which has no influence on the pH, and water. So really, all I need to do is figure out what will be the pH of a system that is 1.5 millimoles of HCl. So here we can do 2 slightly different but very similar methods. I can either figure out the concentration of the protons by using the volume, the number of moles of protons divided by the volume in liters. Or I can make use of the fact that millimoles and milliliters are both multiplied by 10 to the third. So you can also get the molarity of a solution by dividing the millimoles divided by milliliters. It will actually still give you units of moles per liter as you have the cancellation of the millis. So in this, no matter which method you use, you'll find out that the proton concentration will be about 0.043. So in other words, we will have consumed we've consumed a little bit less than half of the protons, but since the volume also increased, the concentration went down by a little bit more than half. So using this new concentration, I can plug that into my pH equation, and we'll find the pH went up by about 0.37 units to 1.37. So despite the fact we added a fair bit of sodium hydroxide, we only had a slight increase in the pH because we still have a strong acid present. And so as long as we have a strong acid present, we're going to have a fairly low pH. And this is an important thing to keep in titrations. The pH still stays relatively fixed as long as you haven't changed the identity of who's the predominant component of the system. So Let's go ahead and see what happens when we change that idea and what would be the pH once I add 25 milliliters of sodium hydroxide. So since my HCl and sodium hydroxide have equal molarities, if I add equal volumes, this will mean that I should have equal number of moles of HCl and NaOH. And since I originally had 2.5 millimoles of HCl, quick math will show that we also have 2.5 millimoles of sodium hydroxide. Now, this is the point at which our limiting reagent problem gets a little bit fun. I will end up consuming equal amounts of both the HCl and NaOH, meaning that we will have reached the equivalence point where both of my initial amounts go to 0. And so I've converted both these species into the net product, in this case, sodium chloride, meaning that I have no excess HCl or NaOH behind. And this equivalence point is actually a very cool feature because I have no acid and I have no base. All I ended up doing was producing salt water. Water plus salt makes salt water in a very expensive fashion. Now from here, since we know that NaCl is essentially going to be neutral, my pH should be that of neutral water. So it turns out this solution has a neutral pH of about 7 because we have no excess acid or base present. So this is a very cool feature of a neutralization reaction, or the equivalence point of a strong acid-base titration. You'll always end up generating a neutral base or neutral solution, which means we automatically know the pH. However, things get a little bit interesting if I add a little too much of that sodium hydroxide. So if I end up adding about 5 excess milliliters of sodium hydroxide, at this point, my moles of sodium hydroxide will now be about 3 millimoles. So I can go ahead and plug that into my ice table. And now we've got a little bit of fun because sodium hydroxide is no longer my limiting reagent. Turns out HCl now will be. So my X will be 2.5. And it turns out the X will stay 2.5 from here on out, no matter how much sodium hydroxide you add. So this will end up producing 2.5 millimoles of sodium chloride, but more importantly, it will consume 2.5 millimoles of sodium hydroxide, leaving about half a millimole of my strong base left. So since I now have the system is going to be contain a strong base, it turns out that this strong base will really dominate the pH of the system, as it's going to be the only significant acid or base present. So we can go ahead and use the amount of hydroxide. And here's one of the big tricky bits, the remaining volume of the solution. Because remember, our volume is no longer 25 milliliters, as we've also added 30 milliliters of sodium hydroxide. So we've essentially caused the system to dilute, as we now have 55 milliliters of water or a solution, or about 0.055 liters. Again, if you want to do the math in moles per liter or millimoles per milliliter, either one is fine, but make sure that your units are consistent. So this gives us a hydroxide concentration of 0.0091. So again, this doesn't seem like a lot of hydroxide until we go ahead and convert it into POH. So by taking the negative log, we find that the POH of the system is about 2, which is actually quite basic. And you can see as we convert this into pH, 14 minus 2 gives us a pH of about 12. So by only adding an extra 5 mils of sodium hydroxide, we sent the pH going from about 7 to 5 in very quick order. So the system quickly went basic. And as you go ahead and using this math, take again another look at our titration curve, you're going to find that the pH is most predominantly determined by which species is in excess. So here in this original point, when we had the acid in excess, so before the equivalence point, the pH is still fairly low, right up to very near volumetrically near the equivalence point. The pH still will keep below about 3. So again, very acidic, you wouldn't want to drink this. However, if you add just a little bit more, you hit that, you go right past the equivalence point and the pH is now very high. and will stay so as you keep adding more and more base, as we're quickly going to just approach the pH of the sodium hydroxide that we are originally adding. So we'll slowly end up approaching a pH of 13. And then we get this very narrow happy point in the middle, where for a quick moment we have equal amounts of base as acid, at which point we get a pH that's neutral around 7. But one of, again, this notable points of the equivalence point is the pH changes very rapidly. So if you're using a pH probe or a chemical indicator, something that indicates pH change, you'll find that you're only going to be neutral for a split second, as the pH is very, very vulnerable to small changes in the amount of strong base added. And we'll go ahead and take a look at how this is both similar and different when we replace our strong acid in our analyte with a weak acid. Until then, take care.